Okay, hello, and welcome to the virtual Lunch and Learn series, which continues. I'm David Brown from Berkeley Nucleonics, and I'm joined by Mark Slattery, who's our Nuclear Applications Manager.
Glad to be here. Thanks, David, for having me in with you this afternoon.
Great. So today we're going to talk a little bit about considerations that we will help you make and trade-offs to think about when we customize your scintillation detector. Before we get started, however, a couple of issues about the webinar. It is being recorded, and we'll email a link to the participants following the event. Participants are muted until the Q&A session. There is a Q&A chat box if you want to put comments or questions in the chat box. If you have an opportunity to expand your window, you'll have a better presentation. We do have some show and tell and some video, and so the bigger your screen is, the better. The chat box is not private, and this presentation is not classified. So certainly you can share the link with your colleagues that might have an interest in custom scintillators. I won't spend a lot of time on the history of Berkeley Nucleonics, but we're very proud of our company and the work we do in the industry. We've been helping customers one at a time for 57 years now, and we reach out into the RF and microwave field, the physics and chemistry and test and measurement fields, and of course the nuclear spectroscopy industry. We do have a network of reps as well around the world. So wherever you are watching this video, there's probably somebody in your area who speaks your language and can help you with ordering, with currency exchange, with support, with calibration. Feel free to send us an email or live chat us on our website, and we'll put you in touch with somebody local who can give you some hands-on support as well. Okay, so let's jump right in. Let's review the trade-offs and factors when selecting a custom detector.
Okay. Sometimes feel very badly that customers will call and they'll be asking, hey, what can you advise? Or I want to do this, I want to do that. And they're asking us questions. And I feel very badly that quite often we have to respond with a long list of questions as well. So these are the types of questions that we will be asking you, and the things that should be considered when ordering, when selecting a detector for your system. One is, we'll ask, well, what kind of radiation are you looking at? What do you want to detect? Are you looking at alpha particles? They tend to be sort of a very high energy, but they're kind of big, they're kind of clumsy, they're pretty easy to stop. They very, very thin materials can stop the alphas. Betas, a little more energy. They are a proton-based, well, essentially they are an electron that when it leaves the orbit, you'll see that it is energetic, high powered, and you'll need a little more stopping power for that. And on the right, the gamma, anytime that the alpha particle decays, anytime that the beta particle decays, gamma radiation is going to be released. And the gamma can travel much further. It is also a very high energy wave. It's a package, it's a photon, and it has no mass. Maybe you remember Roberto Duran, no mass, no mass. Anyway, I'm sorry, I can't help it, my brain works that way. Or neutrons. Are you looking for neutrons? It's an entirely different kettle of fish. It has some mass to it, it's very energized, and can cut through quite a lot of materials. So these are the types of things, and based on the type of radiation that you're looking at, this is what we would advise.
Okay, so I'm going to open up the screen here a little bit so that
excellent
presentation is a little bigger, and let's get into the scintillators.
Okay, now the alpha I'd mentioned, large particle. You don't need particularly thick or very dense materials to capture it. Cesium iodide is very common. The calcium fluoride, also very common. Plastics, as you see over on the right corner of the screen there, the EJ200 is just one variety of plastics. That one's particularly good for the betas. Again, very similar. The cesium iodide, thallium doped, the calcium fluoride, and plastics. The alphas and betas typically are going to be very similar in the type of material that you would want to select. Gamma is going to have a lot more, not so much energy, but a lot more activity. And so sometimes you'll need something that's a little more dense, something that is going to be very bright, something that when a photon strikes it, generates a lot of light internally. And the workhorse, for instance, sodium iodide has been around for a long time. The cesium iodide, sodium doped, is also a very popular workhorse. Very dense and very bright materials like lanthanum bromide and cerium bromide are also tend to be, these are all very common. These are usually easily available. The Neutron, for the Neutron, they are come in different energies. There's the thermal neutrons, which sort of down maybe even in an X-ray region, and intermediate neutrons kind of overflow into the gamma range, and then way up in the fast above 3, 4, 5 MeV, millielectron volts. You'll start needing the lithium boron. Lithium is one material. Boron, various varieties of boron. Helium-3, though technically not a scintillator, but we do want to mention it here because it is available. It is something that we do offer, and it has been very effective for a very long time. And there's probably others that we could talk about as well, but let's just pretty much concentrate now on just these 4 items.
Okay.
People will ask us, well, you know, what should I buy? And so we find out what kind of energy you're looking for, and then we ask, you know, if they have an idea. Sometimes they will contact us, people, and we welcome you to contact us and ask, hey, this is my application. I'm going to be looking for gamma rays. I want high resolution. You may already even know a particular scintillator. You may send us a request saying, hey, I would like, can you give me some quotes on some cesium iodide, maybe 1 or 2 inch sizes of that. And so we will often ask, well, you know, why? What's the reason for it? And so the things to consider are resolution, for instance. Resolution, is it going to be high resolution, low resolution? The average is typically something like the sodium iodide, about 6 to 7% resolution, the energy resolution. How steep are the peaks? How clearly are they displayed and separated from other energies in the same spectrum? Higher resolutions, we're talking cerium bromide. We're talking various lanthanum-based densities also as well. And then there's trade-offs sometimes. Speed is very useful if you know that you're going to be in a very active setting and there's going to be many counts per second. And then you're going to need something that can respond. And so you want something with a very short decay time. This means that it lights up very fast, but it also disappears very fast. And so you won't get a lot of light doing what's called a pileup on the screen. Some of the fastest there's, for instance, barium fluoride, which we have an image there. That's in the picosecond range. The fast component of that is 870 picoseconds. That means that this is a good one for capturing measurements as high as 2 to 10, at least it's supposed to reach up to 10 megahertz. I haven't had a chance to test that myself, but these are very fast speeds. Quite often, most detectors will pretty much limit you to hundreds of thousands of megahertz. Sometimes it's a trade-off there, resolution and speed. So the ones that are very good with resolution may not necessarily be as fast. And sometimes if you want fast, you want speed, you may not be able to get the resolution you want. So it's helpful to at least prioritize what's important in your application. What sort of energy range are you looking at? Are you looking at X-rays? Are you looking way up into the MeV range for neutrons, or you just average gamma range, say 30 keV to 3 MeV? And so there are materials that are better suited for certain ranges than others. For instance, we show here YAP, the yttrium aluminum. Always have a hard time pronouncing that, perovskite, but we just call it YAP. And that's great for low energy gammas. It excels at X-rays, and so that if that's the energy range that you're looking at, then keep that in mind, and maybe we have a suggestion for what's most suitable.
Thank you, Mark. Now, did I goof up? It looks like something's underneath the image on the left. I must have, in my preparation, goofed that up. Is there another parameter below?
Well, see, I had spaced things out, so I'm not so sure. I mean, I don't know if you just like took pictures over and pasted,
Okay.
or
Okay. All right, we'll move on. Dimensions, another critical issue.
Absolutely. People will ask, well, they want a specific size, or they won't even mention the size. Hey, I want this particular material. Can you tell me how much it costs? Is it available? What's the lead time? That sort of information. But the dimensions are very important. Bigger is better in the sense that large detectors will have greater sensitivity in the same way that when your pupil of your eye, the black part of your eye is wide open in the dark, it does this because it wants to pull in more light, and that's really all that these photons are, just a higher energy of light. And so sometimes you want the big one. If you don't have any dimensional constraints, then what's the harm? Let's go ahead and see. Start with something that's 3 inches, 2 inches. They can get up to very large sizes depending on the sensitivity that you need. But you can also go with smaller sizes as well. Sometimes you may have only a limited amount of space to use, and so again, it's important for us to know this so that we can advise whether certain scintillators perform very well at small sizes. It's important to know, for instance, at large sizes, lithium, which is a great neutron detector, but if it gets too large, it starts into what's called self-absorption, and its resolution degrades. So you don't want to get too big if you're using, say, something like lithium. And then there's others like, thinner is better, for instance. You don't have to have a big, or at least certainly not a thick dimension for capturing alphas or betas. Something maybe kind of wide, but thin is very handy. As you can see in the pictures, we have different sizes available for the different jobs. I mean, as small as a pen, as large as what would you guess that is? About the size of a keg? No, that's got to be
Yeah,
smaller.
yards, maybe like a yardstick.
Okay, there you go.
Yeah, call
And
it the yardstick. Yeah,
they're all available. They all have their trade-offs. Bigger can be better, but it's always going to cost more money. You can always rely on that. So again, don't buy more than you really need. We will try to help advise you to make sure that you're getting something appropriate to what your requirements are.
great. And in fact, I'm going to switch on our cameras, Mark, because we have a few samples to show.
Yes, we do.
And that's our test lab in the back. I got to be honest, that's not a live shot. That's our guys. I thought it was a little more interesting than my very boring office. So that's our analog high speed lab where we do some digital work, but analog and digital work. But good. So yeah, I've got one of our nuclears here, which has a 1 cubic centimeter of cesium iodide.
That's probably, I mean,
these are very
I don't know that this is
sensitive.
going to be very sharp here.
Yeah.
But this is the kind of thing. This is a kind of a detector, a cesium iodide detector. It would be ideal for fitting inside of a small handheld portable.
And then sometimes we have some space constraints. So we've got a little box here which fits into some other equipment, and we have a kind of a small chubby detector there, short and fat, and that's used because it had to fit within this sort of backpack-sized enclosure.
And what you're showing there, David, is actually fairly much a very commonly used size. Would be 2-inch diameter and 2-inch thickness. For instance, sodium iodide, and photomultiplier tube for the rest of the space. And more often than not, these are the kinds of sizes that we're using.
So if somebody says, "Oh, I need a 2x2 detector," it's not a 2 square inch. You mentioned a 2-inch diameter by a 2-inch depth.
Yes, they can be square.
Uh-huh.
You can make cubic, but there are. I'm not sure. I think you stumped the chump on that one there, David.
But I think the common when you consider a 2x2 or a 3x3, which are probably the most common sodium iodide detectors, you're talking what diameter by depth.
Yes, absolutely. Yeah, and a lot of times if somebody says 2x2, I usually will assume they're talking diameter first and then thickness.
I got another detector to show you here, Mark.
This is my goodness.
This is a 2x4x16 with a photomultiplier tube on the end.
Attached on the end there, yeah. Yes. That's a good size. And
really heavy.
And it kind of makes me feel sort of, inadequate, so I guess in some instance, you're right. Okay, you're right. Bigger is better.
Okay. Now you've got a 3x3?
I do also, and this is not so unusual as well, a step up from the 2x2, the 3x3.
Okay.
Again, because it's a larger area, a little more dense, it's going to be more sensitive. It's a good choice.
Good. All right. Lots more samples and examples on the website.
Absolutely.
Yep. Okay, moving on. Samples. Go ahead.
It's important to know, what are you going to be measuring? What are the sample sizes to be detected? What is the geometry? Please tell us what it is. Are you scooping up soil or putting food into? This was quite popular and commonly done in Fukushima after the incident in Japan several years ago. Let's test the soil. Let's test food. Let's test water. And so we'll show you some examples of how that can be accomplished. Are you looking at very small activity over very large area? Well, that's true. Then you may have to scoop up large areas and sample them a little bit at a time, or use a very large detector. The 2x4x16 that David was showing a moment ago, the sodium iodide detector, quite common to say mount that portably on something like a golf cart, some type of a vehicle, and cover a fairly large area. Very helpful in remediation. For the food, once it's collected, once it is collected, you may want to put it inside of a lead shield. The idea is you want to expose as much of the scintillator to the material that you're trying to measure. By the same token, on the far right, we show what's called a well detector. Here's an instance where we create the material of the scintillator to surround the measuring area, so we can put a sample of what we're measuring and surround it with the scintillator itself instead of trying to surround the scintillator with sample. This is commonly used for, say, Marinelli beakers or automated samplers, things that run through several moving samples like on a conveyor belt. It's helpful if you're going to be doing the counting on site, or if you're going to take it back to the lab. It's helpful for us to know if you'll be on site outdoors, or if you're going to be doing a lab-based experiment. Soil, food, water, geometry, these are the things that we want to consider because you want to get the best out of the scintillator. So let's optimize distance, geometry, and the size and sensitivity.
Okay.
I was mentioning the samples.
Yeah.
I think we have some things to show you here. Typically, for instance, we might have something like this is a Marinelli beaker. These were used quite commonly during the food and soil sampling after the Fukushima incident. We have like a half-liter size, also a half-liter size, but maybe for different detector sizes. This for a 3x3, a 2x2. And so we fill this with some type of a matrix, the soil, and with the Marinelli beaker, we can now surround the scintillator with the radioactive material and get the most sensitivity, get as much measurement as we can with the space that we have available.
And then I've got the shield to get rid of the background in that same setup, right? So you would put that entire Marinelli beaker and detector in the shield.
That is very important. If we're testing materials that we expect to be very low activity, then we'd want to test it someplace that has a very low background. So we'd want to place the detector inside the shield. We want to put the Marinelli beaker on top and then close the lid, show that that swivels open, swivels closed. So this is quite common for, say, soil sample remediation type activities.
Okay. And quite uncommon to show on a live webinar, I must say.
It's available. You work with what you have.
Okay. All right. Let's move on now. Okay. Yep.
Go ahead.
The operating conditions for the application.
Very important. One of the key questions that we'll ask, what are the operating conditions? Are you going to be using this scintillator, this detector, inside of a laboratory where it's stationary, very regulated in terms of environment and so forth? Or are you going to be moving it around? Is it going to be portable? Are you going to be, we have here an example of the 2x4x16s that David showed, and they can be placed inside of plastic cases and mounted into a vehicle and be used for surveying very, very large areas. But they'll require, I think, a little bit of ruggedness. So this is good for us to know ahead of time. Are you going to be sending it into space? Are you going to be sending it down an oil well? If it's portable, do you want it to be handheld? You don't want something too large. Some people now, this is very exciting, and some people have been putting sensors onto drones and flying them over remediation areas to get a sort of a 3D mapping of which portions of the acreage, which portions of the land being surveyed requires the most attention. So again, stationary or mobile. Consider the environment if you are in a lab, or if you're in a particle accelerator, or if you're performing experiments in other types of physics, high resolution, high powered physics experiments. Will this be exposed to a magnetic field? This is important to know. This will require some special protection for, say, the photomultiplier tube. Will there be large neutron flux? Again, very important to know. Some materials will not play quite as well when exposed to high neutron fluxes. So this is important for us to know, and this is why we ask. Let's see. Anyway, I think I think the rule would be better safe than sorry. Temperature, again, an extension of what we were discussing just a moment ago, the operating conditions. This can affect the light output of certain detectors. Some detectors they're not very linear when they get hot. However, for instance, we've done some experimentation now with cerium bromide. It's doing very well. We've been testing it up to 177 degrees Celsius, 350. That's, baking, your good old-fashioned bake a cake oven temperatures, and these things will still be very linear, still very effective. Besides heat, you might also want to consider the coolness, or what can coolness do. Lead tungstate is a very nice detector for neutron detection, or very, very, very high gamma detection above 3 MeV. And we find that as it cools and starts getting even down to around, as it cools from room temperature to, say, 0 degrees Celsius, it actually starts to improve. Its resolution improves, its brightness improves. And so these are considerations for the type of material. The electronics and the photomultipliers are also affected. So this is not just a matter of the scintillators themselves and how will they respond, but if you're looking at a complete system solution, so it's going to include probably a photomultiplier tube or a silicon photomultiplier, a SiPM. What type of electronics, voltage dividers, do you want preamplifiers? All of these things play into effect. The photomultiplier tubes, very large analog device. They are greatly affected by time and temperature, and particularly temperature. Their center point will drift, and they call it drift. As the temperature goes up, it'll drift a little high. As the temperature goes down, it'll drift a little low on the spectrum, on the gamma ray spectrum. And so if you're going to be exposing the detector that you're choosing to various environments, particularly if you're mobile, handheld, or vehicle, then you want to make sure that you'll have a way of adjusting, of recalibrating, of stabilizing your measuring points while you move from one temperature extreme to another. It's very important that you take that into consideration when you're planning.
Okay. Next slide. Yeah.
Hey, we're always going to ask.
Yeah, of course. Important, very important question. What kind of quantities, and how soon do you need them?
That's important for us to know. We want to get these into your hands as soon as possible. There's advantages and disadvantages to large sizes, things to consider, rather, not so much advantages and disadvantages really, but to consider. The lead times for a large order is quite often going to be a lot longer. And quantities, well, these are the more we have to make. Again, the lead time is going to be much longer. But on the other hand, the price is going to be a little better by using this many photomultiplier tubes, by preparing this many housings. And, we can provide an economy of scale, so it costs us less to produce each individual detector. and that kind of helps bring down the price. We, of course, pass that along to customers as well. We feel that it's only fair. But again, it can be a long lead time, less expensive, maybe a little long lead time. Whereas with a onesie twosie, maybe you just need one or two, and sometimes that's a little shorter lead time. If it's a very common scintillator material, sodium iodide, for instance, and a 2x2, we've talked about that earlier. Sometimes those are available virtually off the shelf. They can be obtained in about a week's time. Some materials are a little more difficult to grow or to obtain, and so sometimes those lead times are to be considered. And the low quantity, I still advise, even if your end result is going to be large quantities, for proof of concept, let's go ahead and maybe do a onesie twosie, run it through the tests, see if it meets the requirements that you have for your application before going with the large quantities. But we will ask because we want to be prepared. We want you to be prepared as well.
Okay.
We ask, do you need a complete system, or are you just looking for the crystals? There are many exotic crystals out there. We get a lot of requests for the lutetium yttrium orthosilicate. That's what we refer to as LISO. You like that one? That was, that's a mouthful. Yeah. We call it LISO. It's a little exotic, and people will contact us to see if it's available, to check out the lead time, what sizes can be obtained. And so do you just want the crystals? Some are hygroscopic. Hygroscopic, we haven't covered that yet. Certain materials should not be exposed to ambient atmosphere. They will attract moisture. The moisture degrades the material itself. And so certain hygroscopic materials like sodium iodide, like cerium bromide, the lanthanums, most of the cesium are either fully hygroscopic or slightly. We will generally require, or at least advise, that these will be encased with, say, a glass window in an aluminum housing, and we will recommend the best way to deliver it to you. But besides the crystal, are you considering a light collection device? We have a picture there in the center of a photomultiplier tube, fairly common device. The detector will fit onto the end where they kind of have the brown surface. It's the bialkali surface, and this is what takes the scintillation photon, the electron, photoelectrons, and starts turning them into real usable voltages like 1, 2, 3, 4, 5 volts. Something we can actually make electronic measurements with. To the right of that photomultiplier tube, I'm sorry, a SiPM. This is a alternative to the photomultiplier tube, the silicon photomultiplier. These are becoming much more available, and the technology is improving. It's new, but it's improving in leaps and bounds. And therefore, with this type of light collection, you can maybe get a good sized detector. Lower right there, maybe a 2x2 detector with cerium, with the SiPM mounted inside as your light collector, and compress the size. With the photomultiplier tube, you might get something a little longer up there in the upper right. This helps us know what your requirements are. We may advise. We are recognized for providing the full package. We are recognized for providing top quality detectors, not just the crystals. We're talking now the light collection, the voltage dividers, preamplifiers, electronics, cabling, connectors. Some people will have very special needs. And so we want to know, are we just looking at crystals? Are we just looking at a total detector? I like to think of crystals as really being just a commodity. you can get them just about anywhere. It's something that you can sort of shop online for. But the whole detector, the finished package, everything that goes into it, that's an art. It's a craft, and that's something that we're recognized as being very good at.
Great. I'm going to jump back over to the other platform here, and we'll get to this last couple of questions, which are
Sure.
top level stuff. The $64,000 question: what is the application?
Yeah, some people are very reticent to tell us what they're doing. Maybe it's top secret stuff, or maybe it's just, hey, it's none of your business. But we really would like to know, are you just going to be counting energies? Are you going to be measuring the energies and performing spectroscopy? Pretty much. Are we just detecting? Are we just going out to see if there is radiation out there? Do we need to identify the isotope? Again, spectroscopy, measuring, resolution, those are all very important. We talked already leading up to this point that there's operating conditions and space and size and temperature and all these things. We've been there and we've done that. We have found solutions for a great many applications. Tell us what yours is. We may have done that already. We may already have a design that meets your needs, and we'd be happy to provide that to you. We may have advice. We may listen to your application and consider a factor that wasn't thought of before, something that just came to mind. And again, we have the experience to look at these vulnerabilities or advantages and disadvantages. But please let us know. After learning what the application is, it may even be necessary to go back over the first 8 questions that we covered before this. Now that we have a better idea of what your application is, let's make sure that we thought carefully about the first 8 questions as well. If what you're going to share with us is, what's the word I'm looking for? Well, if
sensitive material. I mean, it could be a federal program or a state program, or it could be just proprietary to your organization.
Proprietary, that's the word. It's hard getting old. I'm done.
Yeah. Well, I mean, NDAs are commonplace here at Berkeley Nucleonics. We have safeguarding of information. We have firewalls. We certainly have access to clearances that are required for virtually any requirement for a scintillation detector. So, and like Mark said, been doing this for a while and probably have some expertise that might be beneficial. And we want to tap into that. So, like you said, Mark, one last slide.
Please let us know. We want to know.
And then, of course, the big picture, right? So you want a custom scintillator. What's the entire system look like?
Is it going to be part of a larger system? We ask the questions. It's helpful for us to know. What's the detector's role in the overall system? Will the results of the detector measurements have an effect on what the rest of the system is allowed to do? Will the system have to rely on the detector? Will the detector have to rely on what the system gives it? This is typically very important in large high energy physics applications, for instance, a particle accelerator or something where we will be bombarding with neutrons and we want to measure what the gamma emissions are. And so we need to make sure that the device is going to be suitable for that type of an application. Proximity, how close to the source are you going to be? How close to magnetic field? How close to other equipment? What sort of mounting do you need? What sort of housing? We typically do aluminum housing so as to not attenuate the sensitivity of the materials. We try not to do that, but you might need stainless steel, if this is going to be ruggedized, if it's going to be exposed to the elements. this is what we need to know. Proximity mounting.
Collimators, sometimes collimators on the front.
Very good. I'm glad you brought that up. Yeah, this is something that we can provide on the detector as well. For directionality, will you need a collimator to point and focus the energy on a particular point, particular space? We have the resources to help with all of these. Even if you have a technology or you want to explore alternatives, we've mentioned some of the materials, scintillation materials here. There's again our plastics, there's liquids, there are I heard of something called a channeltron, which is a different type of photoelectron converter rather than a PMT. These are all different types of technologies that we have the resources to examine, evaluate, learn about if we have to. But we will work with you, and it may be something that we've already had an interest in, and you kind of forced our hand to divulge that that's something we're already looking at.
So I think what we're seeing here, Mark, is there's a discussion that has to take place, and this is not a shopping cart type of opportunity for the customer, but by having that discussion and sort of drilling into all these areas, the results tend to be pretty good. The results, one last slide here on part numbering, which is another.
This is good.
Yeah, let me give you this one. This is the last technical slide, so I'll let you wrap up on this.
I'm just glad you included it. What this does is illustrate the model that you get pretty much explains the model that you have, the features, the functions, and what it contains. And this is really an example here of consideration of all the variables, all of the choices, all of the details, why we ask these questions, because what size, what geometry, what shape do you want it? What scintillator in diameter or in something something other than a cylinder, other solid structures. What type of a device do you want to use as your light collector? Do you want it to be detachable from the light collector so that you can move different types of crystals onto the same PMT that you have installed in an application? What kind of a window do you need? Quartz to help focus? Just regular glass? Do you need maybe something like a mylar or a titanium, very thin type coating window to keep alpha energies out while you're focusing more on a different scale, a different energy range? The electronics, the PMT, you need a voltage divider. Do you need a negative bias? And this is important, particularly if you're interested in fast. If we are talking about something in the megahertz particularly, you'll need to have that bias voltage in the negative, and almost an entirely different topic unto itself, something that we can't go into detail here. But this is something to consider, and we will remind you if you're telling us that speed is very important. Extra features, we'll have a built-in thermistor, some of the features, fiber optic. Do we need to guide the photons or the light to in a less than linear, less than straight-on fashion? Do we want non-standard or custom configurations? Do we need to select special low background materials or low hydrogen materials, even in the case for neutrons? So these will be, this is why we ask. This is a result of everything that we ask. And as you can see, there's a lot to think of, a lot to consider. That's why we ask.
Great. So at the end of the day, you will get a part number. You will get a drawing, a price that's competitive, and it'll take a little bit of give and take, but I think we know the end results are worth that extra energy up front really refining the need to the application. We spent quite a bit of time going over different issues, but we do have some additional webinars that have been pre-recorded, and those are available on our YouTube channel. There's a couple of really fascinating webinars that cover all the nuances of the different materials that Mark was talking about. You know, the different types of packaging, the different types of geometries. There's also a webinar on SiPM technology, which is a new silicon photomultiplier technology, which replaces a PMT tube, and when that's worth the trade-off and when it's not. After you've watched those webinars, you may still be craving more knowledge. So we have an academy. We have classes on nuclear detection, on the basics of radiation and everyday life, nuclear medicine, detecting thermal neutrons. So those courses are all available at the BNC Academy. And because you've spent this much time and gone through this particular webinar with us, we're going to definitely give you the registration code for the Academy so you can take any of those courses.
Ooh, your reward.
No cost. So register code is Berkeley, and you just jump into the Academy at academy.berkeleynucleonics.com, and you can access any of the courses there at no cost. So we think that's a fun way also to develop more knowledge about the world of nuclear electronics and nuclear materials. Good. So this kind of concludes the webinar, and we will leave time for questions and answers, and anybody who has still like to dig deeper into their specific application. So
yes, welcome callers. We do take requests, but sometimes we have to give the answers offline. So.
Yeah, and thank you, Mark, for your time today and for answering so many questions.
Happy to, David. Thanks for having me along. I've enjoyed it. Everybody out there, take care. Thanks for tuning in.
Okay. So